Thank you, Stuart. This feels both familiar and unfamiliar. I'm usually sitting down there looking at the screen. Tonight I'm going to take you on two journeys around the world. I'm going to take you on a journey that stretches back a little over 150 years. And if we have time, I'm going to take you on a journey that stretches into the future and that is relevant to all our lives. It draws on research that I've done in the past 10 years. And it's particularly relevant at the moment because 150 years ago, a ship called HMS Challenger went around the world, measuring for the first time what happened beneath the surface of the ocean. That's not particularly exciting because everybody knows about it. It's been well researched. But when I started to look at that data, I found that another ship had gone round the world at the same time. A ship that people knew almost nothing about, and yet which made very similar observations. And so this is the story of both of those ships, of the data they collected, and of its relevance today. So we're going to have some historical background. I'll talk about those two round-the-world voyages. Then we'll talk about health and safety, not as it pertains to us. We'll talk about climate change and the legacy, and if we have time, we'll go into how we monitor the state of the oceans now based on what happened those many years ago. Actually, I'm just going to put my timer on so that I can know. There we are. We started. So first of all, I'm going to go back a little more than 150 years ago to a couple of pioneers. Now, across the top there's a little bar. So the box there corresponds to the time that those two voyages went around the world, and the two dots and the dots you see appearing there relate to the topic of that slide. So these were two pioneers. The first one on the left, a chap called James Rennell. He signed on as a naval officer. He was a surveyor and ultimately became the surveyor of Bengal, working for the East India Company. And of course that meant that on quite regular occasions he had to sail on ships from the UK out to India and back again. And being a naval man and a surveyor, he started to take an interest in the currents and the winds that were encountered and started to document them. And in fact, in 1850, actually just after he died, his daughter Jane published a book called "The Currents of the Atlantic." Published in 1832, based on his observations, and there's one of the charts from his book. On the right is, in a sense, his counterpart a little later on in the United States, somebody called Matthew Fountaine Maury. He also had been a naval officer, and then he took to effectively carrying Rennell's work a little further by looking at ships' logs and documenting in a very systematic way the currents that were encountered and to some extent the temperatures and the winds as well. His motivation was not entirely academic because the area that he was interested in was the Atlantic, and there was a huge amount of trade between the UK and the United States, and steamships were starting to come along, and so if you understood what the currents were going to be, you could avoid currents that were likely to be against you, and you could work with currents that were in your favour, and you could make money and save money. So Maury, in effect, was the real pioneer, because he started the systematic mapping of information about the surface of the ocean. Now, that's all very well. People have been looking at the surface of the ocean for hundreds of years, ever since people have sailed on it. But what happened below the surface? Nobody knew. Animals came to the surface from time to time and were seen. And of course, nature abhors a vacuum, and so people came up with theories of what there might be below the surface of the ocean. And here were two of the people who postulated those theories. On the left, Edward Forbes, a zoologist from the Isle of Man, and his theory, based on really very little evidence, was that below about 300 metres nothing could live. There would be nothing living on the bottom of the ocean. On the other hand, Thomas Henry Huxley, a little later on, based on some samples that had been dredged up and looked at in the laboratory, decided that probably the bottom of the ocean was completely covered with some primordial slime called bathybius. But of course, nobody really knew, because nobody had made any real observations at the bottom of the ocean. And three more people decided it was about time to find out. They were William Carpenter, Charles Wyville Thomson, and John Gwynne Jeffreys. I haven't got a photograph of him. They used two rather antiquated naval ships, HMS Porcupine and HMS Lightning, and mounted some observations around the north of Scotland, west of the UK, and also in the Mediterranean. And to do this, they actually designed equipment specially made for it. A picture of it on the right, a sort of dredge that you could dredge along the bottom of the sea, and there was also, they had some primitive thermometers, and they could take samples of the water and analyse them. And they found that there were indeed things living at the bottom of the ocean, and so that disproved both of the prior theories. So this is sort of whetted people's appetites, and the motivation for it was not entirely academic. There was developing a great interest in what happened at the bottom of the ocean. And that was because the first telegraph cables were being laid across the ocean. The telegraph on land had revolutionized communication, but the idea of communicating between continents was a really tantalizing thing that held tremendous potential, perhaps a bit akin to artificial intelligence today. So the thought was, well, we'd better start to find out what is at the bottom of the ocean. How deep is the ocean? What's the bottom made of? What lives there? Are our cables that we're going to lay safe? And there was a huge amount of money being invested. The Brunel ship, the Great Eastern, had been converted so that it could carry the huge amounts of cable that were needed. The other thing that had happened was the Suez Canal had opened. That sort of speeded up the passage of ships to India, but it was really telegraphy that was going to make a huge difference. So, based on the experience of the Porcupine and the Lightning, to cut a long story short, a letter was sent from Dr. Carpenter to the First Lord of the Admiralty, urging the dispatch of a circumnavigating expedition thoroughly equipped and with a competent scientific staff to traverse the great ocean basins and prepare sections showing their physical and biological conditions along certain lines. Well, that was quite a challenge. It had never been done before. But then, as now, with any big enterprise, the first thing you do is set up a committee. Actually, they set up two committees, one from the Royal Society and one from the British Association for the Advancement of Science. And as a result of that, the Admiralty assigned a ship to do this job. And here she is, HMS Challenger. She was a Pearl-class naval corvette. She'd been launched in 1858, 69 metres long, and she normally had a complement of 290 people. Think of 290 people on a ship only 60 or so metres long. For the voyage, they'd removed most of her armament from, well, I'll tell you in a minute, down to 2 from an original 8 major guns. She obviously had to undergo a major refit to make space for all these scientists and their equipment. And there was a huge amount of equipment to be put on board. To mention one thing alone, the ship was to carry 885,000 fathoms of sounding line. That's 100 miles coiled up and stowed on board, together with all these heavy sounders and dredges and all kinds of things like that. Her complement ultimately was reduced by 60 to a much lower engine. She had an engine. You can't see her smokestack there, but it's in there. And if you wanted to see a ship of comparable age, go to Portsmouth Dockyard and have a look at HMS Warrior. Similar age, much bigger ship, but that one built of steel. Challenger was a wooden ship. Thought it might be interesting. Oh, the other thing to note, which is relevant for later on, because she had an engine, coal-fired boilers, they could make their own water. They could distill seawater and make fresh water for the crew to drink. And that removed some of the hazard of taking on dodgy water from all kinds of ports around the world. I thought by comparison I would show a more recent ship. The Royal Research Ship Discovery, based in Southampton, launched in 2012. 99.7 metres long, beam of 18 metres, so considerably bigger than Challenger, but with a total complement of only 52. Challenger was crowded. The officers had quite reasonable accommodation. The crew existed on salt pork, salt beef, ship's biscuits, and that was the standard naval fare of the day. Let's meet the scientists and officers who took that voyage around the world. First of all, Captain George Nares. Now he really had considerable experience of expeditions. He'd been up to the Northwest Passage looking for the ill-fated Franklin expedition. He'd been at the opening of the Suez Canal, where he made a bit of a name for himself. The idea was that at the opening of the Suez Canal, the French Royal Yacht would be the first ship to traverse the canal, as was appropriate because the Suez Canal was very much a French project. Nares managed to get his ship, the Newport, ahead of the French Royal Yacht. And of course, there's no room to overtake. And so it actually was a British ship that was the first to traverse the Suez Canal. He got rapped over the knuckles and recalled to London and was told off, but it didn't do his stature in the Royal Navy any harm. Also aboard was Captain I should say that Nares decided that this was such a fantastic opportunity to go on a cruise round the world, first one ever scientific expedition. He would take his 9-year-old son along with him, William, be good for his education, take a schoolmaster along with him. Actually, wasn't actually that unusual, because remember, there were quite a lot of cadets on board who were probably about 14 years old, so he would have been younger, but not significantly younger. I don't know why my thing is still going. Anyway, right. Frank Thompson. He took over from Nares when Challenger reached Hong Kong. Nares had been recalled to lead a British expedition to the Arctic, and by this time Thompson knew the ropes. Sorry for the pun, but it was clear how to run this scientific expedition. Thompson then took over and went on later to actually command the Royal Yacht, the Victoria and Albert. What about the scientists? Well, the first one was Charles Wyville Thomson, who we've heard of already. So he was on the Lightning, and he was trained as a medic, but became a zoologist based in the University of Edinburgh. By that time, the time of the voyage, he was already a Fellow of the Royal Society. Those are their ages at the time the ship sailed. He was Professor of Natural History at the University of Edinburgh. Right. This was an international group of scientists. The next one is John Murray. Born in Ontario, came to Edinburgh at the age of 17 to do a degree, first of all in medicine, but then became a zoologist. And he had actually spent some time in the Arctic on an expedition going up into the Arctic on a whaling ship called the Jan Mayen. So he had some experience of working in difficult places. His job was to bring together all the equipment that would be needed. Now here is John James Wild. Actually, no, his real name was Jean-Jacques Wild. He was Swiss. 46. He was the oldest of them. He was the ship's secretary, and he was also the illustrator. And here I should say something about illustration. The Challenger expedition was the first to carry photographers. There are lots of photographs of posed people like that. There are lots of photographs of the landscape at ports that they went into. There are no photographs of people doing things on board, and there are no photographs of the samples that they took, because that was too difficult. It took too long a time exposure or needed a specialist camera. So all those other illustrations were done by hand, and there's a book over there that you can have a look at. You will see that those illustrations are absolutely fantastic. Then Henry Nottage Moseley, well connected, educated at Harrow School. From a very early age he was besotted with natural history. He was quite young, 28, and he joined the crowd. He was also I think he was at the University of London then, and all of them had bushy moustaches and beards, a qualification for being an oceanographer perhaps. he was very enthusiastic. It's said that he was always the first to offer to do anything. Now, here's a man, John Young Buchanan, a rather dual person, but in a sense my hero, because as we'll see later, some of the measurements that he made were fantastically good. He was the ship's chemist. 28. And finally, Rudolf von Willems-Söhm. He came from Schleswig-Holstein, on the border between Germany and Denmark. He was aged 25, so very young. And it's rather interesting the way that he came to be on the expedition. He'd been working with a Danish expedition north of the UK and happened to come into Edinburgh in October 1872. And he knew Wyville Thomson and went to see Wyville Thomson, and Wyville Thomson invited him to dinner and was so impressed with this young man that he said, look, take yourself down to London, get yourself, talk to Huxley, and if Huxley says it's okay for you to come, you can come on the voyage. So within 10 days, he'd been interviewed, passed the test, came and was the youngest person to sail on the Challenger. So where did it go? It sailed on the 21st of December 1872. It sailed from Sheerness. The start was not auspicious. One of the crew fell over the side and drowned ahead of them leaving. They encountered a horrible westerly gale, and the crew were not best pleased and actually let it be known. So we have, as well as the reports, we have lots of diaries that came back from the Challenger, and one of them reports that the officers had a grand dinner at 6 o'clock and a turkey very mysteriously disappeared just as it was ready to go on the table, and it was never heard of since. Again, last night a roast goose and 2 loaves of bread were taken off. Off the cook's table before the cook could turn round. Some fragments of the goose were found this morning up in the top rigging where the goose had been taken and devoured. The officers made a kick-up about it, but couldn't find out who took them. So there was a bit of a them and us. The officers had turkey and goose, and the ship's crew were existing on salt pork and salt beef. So the ship eventually set off and started its routine observations. And here's some pictures of them doing it. Notice no photographs. Lowering equipment over the side. That actually is an accumulator. It's a big elastic band, effectively, to stop the equipment bouncing up and down. There in the middle, samples of water being taken. And on the right, the officers and scientists actually sorting through the stuff that had been dredged up from the sea floor, rocks and animals. The crew found this extremely boring. The scientists call it dredging, the crew called it drudging. But a huge amount of samples was collected and stored, and the temperature of the water was taken, and samples of water were collected and analysed. Typically, the ship would be on what we'd call a station. So if we go back, each of those dots along the line is what we call a station. That's where the ship stopped and made the observations, and it would be at each of those positions for about 12 hours. Starting at first light, when the ship's sails would be furled, the engine fired up to hold the ship in position, and everything lowered to the seabed. There were 352 of those, And actually the total distance they went was 3 times round the Earth's circumference. 728 days at sea, 520 in port. And they actually went to some rather pleasant places. Here's a sort of couple of pie diagrams of the outward and homeward voyages. The grey bits are when they're ashore, the coloured bits are when they're at sea. So they're in Cape Town, Simonstown in South Africa, Bermuda, Halifax, Nova Scotia, the West Indies, Sydney, long time in Japan where the ship had a refit. It was not too bad. Right. Now, so that's the famous voyage. When I was doing my research, looking at the temperatures and the salinity data that had been collected by Challenger, I became aware of another ship going round the world at the same time. It was a German ship. Now we'd better have a bit of geopolitics. The Franco-Prussian War had happened from 1870 to 1871, and following that Germany became a united country for the first time. Britannia, as we know, ruled the waves, and the Royal Navy was the envy of Germany. Germany didn't really have much of a navy. It hadn't performed very well in the Franco-Prussian War, and so this new united Germany was looking for an opportunity to actually show that it could be a naval power. The other thing that was motivating Germany was it didn't have any colonies. Britain had lots. So was there a chance then to send a ship around the world, a German ship, to answer some of those questions? And there was a good excuse for doing it as well, because in November 1874, there was to be a transit of Venus. So Venus going across the face of the sun. And if you went to the right place in on the Earth's surface, you could observe it. And a good place was down in the South Atlantic Ocean, or Southern Ocean. And so this gave them a motivation for sending a ship around the world. And here she is. Well, it looks very much like the Challenger, doesn't it? And here's the comparison. A little bit longer. Gazelle was 72 meters, Challenger 69. Big difference. Challenger reduced her complement. On Gazelle there were 338 people. There was only one scientist. This was very much a German Navy expedition. And they only reduced, well, they didn't reduce their armament, they still had 8 cannons. There are some clues in the orders that were given to the ship's captain as to what the motivation might have been. SMS Gazelle must retain the character of a warship. So this was clearly, this wasn't perhaps going to be a scientific expedition, but it was a round-the-world voyage by a warship. Please avoid any demonstration which could give the inhabitants the impression that you are pursuing political aims. Well, that's a bit of a giveaway, isn't it? And here's where she went. Not quite the same track. She headed off straight down through the Atlantic, called into Cape Town, then went across to Kerguelen, some islands in the Southern Ocean where they would drop off the party of astronomers who would observe the transit of Venus, and then The ship would wait there all that time while they were doing it, pick them up, take them to Mauritius, and from Mauritius they would then go across the Indian Ocean and spend quite a lot of time around New Guinea, because that seemed a possible good place to look for a new colony. They would then go into Australia for a bit of rest and recuperation, then across the southern Pacific, round Cape Horn into Montevideo in Uruguay, where actually she met up with Challenger, quite by chance. They were both there at the same time, and they met and they agreed to take different tracks back to Europe, arriving back in April 1876. So, now, in what follows, I'm going to draw very heavily on a paper which I found, written by a chap called Volker Hartmann, written in German. All the reports of the Gazelle expedition were in German, but this one, he was a medic in the present-day German Navy, and in 1995 he wrote a paper about the health on the Gazelle. But let's go back first of all to what happened on the Challenger. Challenger reported that the health of the ship's company during the commission of nearly 4 years must be regarded as exceptionally good. There were, however, 7 deaths, two drowned, 1 killed by an accident. Fortunately, a rope broke and it killed one of the crewmen. 2 by natural causes. 1 was William Nares's, the 9-year-old schoolmaster. So that didn't turn out well, and he actually came back eventually to the UK. And sadly, Rudolf Wilhelmus Söhm, he succumbed to boils. Now, these days you'd just treat them with antibiotics and he'd be cured, but shortly after leaving Hawaii, he was taken very ill and died within a few days and was buried at sea. So sadly, this very bright young man never made it to the end of the expedition, and 2 died by acute poisoning, 1 alcoholic poisoning. There were quite a lot of desertions. As I said, the ship went to some quite nice places where they spoke English, and it probably seemed like a better offer than going around the world any further. There was no scurvy on board. So let's come back to Gazelle's voyage. So here we are off Kerguelen. They were there for 103 days. The average temperature on this unheated ship was 4 degrees, constant gales, and they had nothing to do. So that was pretty miserable. Then they went across, as we saw, to New Guinea. New Guinea had its own challenges. It was warm, but there was no wind. And very soon they ran out of coal. So the only way they could move the ship was to send the crew ashore to chop down trees to feed the boilers. And on those long expeditions ashore, they didn't take water with them. They drank whatever water there was, and they got ill. So they got malaria, they got yellow fever, they got all kinds of nasty things. And they were around New Guinea for 56 days. Now, there's certainly some evidence. First of all, accidents in the rigging also occurred, not infrequently. A large number of bone fractures, ligament ruptures and dislocations. And that was even before they got to Kerguelen. By the time the ship reached Australia, it was quarantined. The symptoms of scurvy were commonplace. 7% of the crew were sick in the bunk. On some days, more than 50 people were not able to work. They had yellow fever because we had so many fatalities, and there were still 56 people we were quarantined, and scurvy. Now, scurvy. Dental gum afflictions were repeatedly observed, so that by the time the ship arrived in Australia, the danger of scurvy epidemic was imminent. Well, the Royal Navy knew how to stop people getting scurvy. Actually, the German Navy did too, but they were a bit penny pinching. They knew that lime or lemon juice would solve the problem, but that was pretty expensive stuff. So instead of that, they had, and I think we have a slide. Oh, well, no. What they were given was pickled sorrel, vinegar, and citric acid. Citric acid tasted much the same as lime and lemon juice, but of course it had no antiscorbutic properties. So there was scurvy, and indeed the last entry in the report of the cruise was, "Thank God this difficult and arduous journey is behind us." Now that actually is the clue to why one of those ships became famous and the Gazelle expedition was really forgotten about. Everybody was happy that it was over. There was one scientist on board. All the others were ship's officers and crew who were assigned to other ships. So there was no one there to look at the data after the ship got back. It was well documented, German efficiency, everything was written down, and I can show you over there some of the reports with every measurement recorded in great detail. So what did those measurements show? Let me just see how the timing is going. Okay, we're all right. First of all, I'm going to talk a bit about the timeliness of those voyages. Why were they worth looking at? What you see here is a picture of the amount of carbon dioxide in the atmosphere over the past 1,000 years. Running along at about 270 parts per million, and then starting to rise, and then you see the measurements that are made today, still being made at Mauna Loa in Hawaii, and going up to the present day value of, let me go there. At the start of the Industrial Revolution in 1800, about 266 parts per million. Nowadays, 422, and rising at the rate of about 3 parts per million per year. And when were the Challenger and Gazelle expeditions? Right there. So those two expeditions provide us with global scale observations very close to the start of the Industrial Revolution, very close to the time when we, by driving cars and burning fossil fuels, started to affect the atmosphere. And so that's why they are important. They give us a glimpse of what the ocean was like pre-industrial era. And just to show you the observations that were made by lowering instruments into the water for Challenger and Gazelle. And what you see here is a whole lot of lines, each one for the station. So these are the station numbers along here, and the vertical dots are where in the depth of the water column observations were made. And obviously, to start off with, in the North Atlantic, they weren't making very many. They were still trying to find out how to do it properly. They made quite a lot of observations near the bottom, but eventually they started to make them systematically at a range of depths. Gazelle again had measurements near the bottom, but only a couple near the surface, at surface and 200 meters. We need a little bit of an education here. about why the vertical distribution is important. This is an explanation of what all we oceanographers know as the thermocline. Thermo, temperature, cline, gradient. It's where there's a gradient between warm water at the surface and cold water deep down. And it's really in two bits. There's a sort of permanent thermocline, which goes up to probably about 500 meters or so. And then in the upper layers, there's an area which warms up in the summer and cools off in the winter. And that's called the seasonal thermocline. Temperature scale for those at the back, going up to 20 degrees at the surface, but in the at high latitudes, it's basically just a few degrees, effectively from top to bottom all year round. So that's why the distribution of observations in the vertical is important. And what do the observations look like? Well, actually, here's some modern observations. Imagine you're standing in Gibraltar and you're looking out at the Atlantic Ocean. You have very wide-angle vision. You can see all the way from the Arctic to the Antarctic, and you're looking at a slice through the middle of the Atlantic Ocean, down from Iceland down to the Southern Ocean. And you take all those temperature measurements and you color code them according to how warm or cold they are. And this is what it would look like. So here's the warm water at the surface. Here's the cold water, which you can see is coming and filling the bottom of the ocean from water formed in the Antarctic. And some more cold water coming down from the Arctic and cascading down. So that's the kind of picture that we get today. What kind of things did the Challenger manage to measure? And I'm going to focus on the Challenger basically because their observations were better distributed. So here's a line from Bermuda, from Halifax, Nova Scotia, to Bermuda, to St. Thomas in the Caribbean. And here's a plot of the stations, and they contoured plot. So this is effectively just like the one I showed you. And one of the features that it shows is a blob of water which is about 18 degrees Celsius. Actually, they measured everything in Fahrenheit, but never mind. 18 degrees Celsius. And indeed, that is exactly where we see 18-degree water today. So their observations, although the thermometers were pretty primitive, actually did map out some of the major features of the ocean. And here are those observations overlain with it, and the dots represent the difference between modern day values and the 1870s values. Some warmer, some colder, rather noisy. But if you average the whole lot, so you take every station that was measured all around the world and you average the temperature difference between modern day temperatures and old temperatures, what you find is that the water at the surface has warmed by about 0.6 of a degree and getting smaller and smaller differences until by the time you get down to about 2,000 meters, the temperature the Challenger measured was basically indistinguishable from what they had today. So they did a pretty good job. 40 minutes, okay. Right, now to my hero. Dour gentleman, John Young Buchanan. Doesn't look like a person you'd want to take down to the pub for a drink, does he? But he was a very good chemist, and he was extremely diligent. So one of his jobs was to measure the density of seawater. I've been talking about salinity. That was a poorly defined concept in those days, but they did know that the density of seawater varied. So why don't you measure the density of the water you collected, measure the temperature accurately, and how do you do it? Well, how do you do it on a ship? That's pretty difficult. He actually did it in the same way that all you home brew makers do to know whether your home brew is ready, they used a hydrometer. But they hung it from a gimbal table, and here's an artist's impression of John Young Buchanan making those measurements in the lab. He locked the door. He locked the door every time to make sure he wasn't disturbed. If the ship was bouncing around a lot, he delayed making the measurements. He delayed it if it was very windy and drafty. So he was very, very careful. I then set about with my friend Stuart Cunningham, who some of you know, looking at how good those measurements were. We expected nothing. You know, would you really? So here's two plots. The red line is along the Challenger track. What's the present day salinity at the surface of the ocean? The black line, with a sort of fuzzy grey area about it, is the measurements that the Challenger made, Buchanan made. They basically follow the same track. They show all the major features. So here's going into Nova Scotia, where there's very fresh water. Here they're going into off Brazil. So here's the Amazon fresh water. Here they're going down to Antarctic, again fresh water. Off Cape Horn again, very fresh water. And into the Atlantic, where salinities are high. And the difference between those two curves is actually significant. We were amazed. And how do we know it's significant? Right, I'm going to ask you a question. Do you know how people measure rainfall? Yep, anybody? A rain gauge. Right, think of trying to do it at sea, where there's always spray and everything's bobbing up and down. It is almost impossible to measure rainfall at sea. But what you can do is measure salinity. And here's a picture of the surface salinity of the present day ocean. Color coded again, so the salty areas are dark red, the fresh areas are pale in the north and south, and there's Challenger's track. And what we discovered was that we knew from recent measurements that the salty areas of the ocean are becoming saltier and the fresh areas are becoming fresher. And we attribute that to an amplification of the hydrological cycle, the cycle by which water gets evaporated from the sea surface, goes up into the air, forms rain and falls elsewhere. And so what we actually managed to show was that the way in which the signal, this sort of high-low salinity pattern has amplified over time, has accelerated. So we looked from the 1870s up to the 1950s, and then from the 1950s up to the present day. And we could see a slow change for the first 80 years, and then a much faster change. So it sort of reinforced the idea that the hydrological cycle of exchanges between the atmosphere and the ocean had accelerated. We never expected that to be possible to see. And finally, in this part, they had all these wonderful samples that they put in bottles and took to the Natural History Museum. And some of them are valuable today. On the right, you can see electron microscope views of some plankton forams with a calcium carbonate shell. Just look at the ones on the right. The bottom, oh sorry, I pressed the wrong. The bottom is one of these from the Challenger expedition with a nice thick shell around it. The top one is another one typical from the same area, same depth, a much thinner shell. A sign that the ocean is becoming more acidic and these plankton are finding it harder and harder to form their shells. So, Challenger's legacy. It took 20 years to compile all the information from Challenger into these 50 volumes on the right. Here's a much lesser set from the Gazelle. Probably all the samples that were collected by the Gazelle were lost during World War II. But these samples still exist and are still available for analysis. The data are still available, some of them online, not all. Some of them you have to delve into the old reports to find out. And what's left of the two ships? Oh, I should say, actually, if you go to Edinburgh, they set up an office in Edinburgh, in Queen Street in Edinburgh. So if you go to Edinburgh and stay in the Travelodge in Queen Street, it's right next door to the office where the Challenger expedition compiled all its data and published all these reports. And the only thing that's left is the figurehead of HMS Challenger, which graces the entrance lobby to the Southampton Oceanography Centre. So I think we've had, well, how long have we had? Probably
about 50, get over 50 minutes.
Can I have 5 minutes?
Yes.
5 minutes, right. Yeah, bonus. Okay, there's the paper that I wrote about comparing the two voyages. Right, monitoring the oceans. So in a sense, Challenger and Gazelle started the collection of systematic data from the oceans. So if you took the period from 1851 to 1900, and this is all the data that's in a database in America, in Washington, D.C., you'll find that there are a total of 261 stations with observations that went as deep as 2,000 meters. Not very many. How about the next 50 years? Well, it's not much better. There were only 4,500, most of them in the North Atlantic, a few in the Pacific, quite a lot in the Southern Ocean. The discovery investigations mounted by the UK to look at the ecology of whales in the Southern Ocean. But large areas of the ocean completely unobserved. 1951 to 2000. Well, we were doing quite a lot better then. You can see that people still did lines across the ocean. You can see the lines, but there's still great holes there. Only a matter of 2,000 observations in any year. Early on, people doing just the same as they did on Challenger, collecting water samples, reading thermometers, but later lowering electronic instruments into the water column and measuring remotely. Then, from 1990 to 1998, we were really getting worried about climate change. So all the major oceanographic countries of the world came together to do a thing called the World Ocean Circulation Experiment. And this is just one bit of it. This is the bit that did the kind of thing that Challenger and Gazelle did, measuring temperature and salinity and lots of other things. And this is where the measurements were made. And in those 8 years, 18,000 stations, about 2,000 per year. Then we entered the robotic era. Here's a fleet of almost 4,000 robotic instruments which are drifting around at 2,000 meters, Every 10 days, every one of them comes to the surface, measures temperature and salinity. I should say salinity nowadays is measured by measuring the electrical conductivity of the seawater. They send the data up to a satellite, go back down again, drift along for another 10 days. Some of them have a lifetime of 7 or 8 years. This is harder than space science, much harder. But it's generating 137,000 profiles a year. So we really are, there are no holes in the array. You could say we are data rich. And what do you do with that data? You can calculate the amount of heat that's being stored in the ocean. And here is a plot based on those measurements for the top 2,000 meters of the ocean. And it's the scale is zettajoules. That's a joule times 10 to the 22nd, so with 22 noughts after it, and increasing by about 10 zettajoules per year. And 10 zettajoules is enough to raise the temperature of a billion, a European billion, 1,000 million Olympic swimming pools of water from 0 up to boiling point. So that's the amount of heat that's being stored in the ocean each year. 90% of the excess heat that we're causing by global warming is actually stored in the ocean, and it's a huge amount. And that's it, and it's important because that is driving sea level rise. That is driving 2/3 of the rise in sea level. And now I'm going to frighten you with a picture. You can all go to this place. It's called climatereanalyzer.com. And it's a monitor of the average temperature of the surface of the ocean. And it goes back to 1980, I think, yes. And these pale lines are the past measurements. Where's my pointer? Oh, it's still there. So those are what we've had over the past 20, 30 years. This is the last 2 years. Here's 2023. Look at the difference between that and anything that's gone before. And here's 2024. The same. If this were an electronic circuit and you were looking at the output, you'd say something had broken. This may be a very strong indicator that something is broken in our climate. So over there are some books for you to look after. I'm happy to answer questions. And here we are. Thank you very much.